Okay, there is one very interesting duality between the time and the frequency domains, which we should try to master. It's a way of uh, kind of becoming expert in switching back and forth from the time viewpoint to the frequency domain viewpoint. And this duality relationship says that if there is certain signal whose time domain representation is given by the small x of t, and after Fourier transformation it becomes capital X of f, then if you have another signal which is capital X of t, its Fourier transformation is given by small x of minus f. Uh, and I will let you prove this yourself. A hint is that what matters in the Fourier transformation is the product f times t. As long as that product remains the same, the answer doesn't change. And so you can interchange the role of f and t, and you will still get the same exact identities that you would have gotten otherwise. Um, okay, um, so this is a very interesting and very important relation. It is called the duality relation. So fine. So what do we mean by this? I mean, what is the use of this duality? So let us apply this duality to do some very quick derivations of some additional Fourier transformations. We can quickly derive some new Fourier transformation relationships. Uh, so first, right away, we'll take this example that we had in the very first example, that the Fourier transformation of the complex exponential phasor at f of c is just direct delta function located at f of c. But now what this duality relation says is that I am allowed to switch the meaning of time and frequency. I can flip it. I can change uh, what is time here and what is frequency here. I can change it. And so when I change this, instead of calling this as belonging to frequency domain, if I call this as belonging to time domain, it becomes a time domain impulse. And that time domain impulse is given by this expression here, delta of t minus t of d. Why did I change f of c to t of d? Because in frequency domain, what matters is some carrier frequency f of c. In time domain, when I'm looking at an impulse, what I want to see is how much delayed that impulse is in time domain compared to time of 0. And so t of d represents the delay, t of delay. And this would be specified in terms of seconds. This f of c would be specified in terms of hertz. So basically this delta is my capital X here. But I'm using the same capital X, but I'm considering now it as a function in time domain. And what I want to see is what is the Fourier transformation of this delta of t minus td. Well, the duality relation says that the Fourier transformation is going to be same as my small x, except wherever there is f, I have to replace it by minus f. But the small f is this here. And so now when I replace f by minus f and t by t of d, then this becomes my Fourier transformation pair. So delta of t minus td is nothing but this function here. So now I will ask a few questions to you. You can think about it yourself. That what is the magnitude of the Fourier transform of delta t minus td? What is the magnitude? Remember, the Fourier transform has to be specified as a function of frequency. So you have to tell me what is the magnitude of this Fourier transform for different frequencies, not just for one frequency. What is the phase of the Fourier transform? And then finally, what is the complex valued Fourier transform of delta t minus Td? You can get all these three answers by looking at the Fourier transformation, which is already specified here. All you have to do is fill in the blanks by looking at this expression here. But more importantly, I think at least for the magnitude and phase, what you want to do is not just fill in the blank, but also draw a picture similar to what we had on the previous slide. Okay. Now, once we come to grips with this duality between time and frequency domain, it, it gives us a lot of conceptual power. And so basically everything that we kind of understand or we prove in one domain, we can quickly apply the duality principle and say that the same thing must be holding in the dual domain. So one way that we can extend what we have done earlier, which is that convolution in time domain is equivalent to product or multiplication in the frequency domain. We went over quite a detailed reasoning to convince ourselves why the first sentence is true. But now that we have kind of proven to ourselves that this first statement is true, convolution in time corresponds to multiplication in frequency, then right away, because of this duality relationship between time and frequency domains, right away we can change time to frequency and frequency to time and say that if we are having two time domain signals and we are multiplying them in the time domain, in the frequency domain, their Fourier transforms or their frequency spectrum must be getting convolved with each other. So this convolution and multiplication works both the ways. In time domain, if you convolve, in frequency domain, you get multiplication. But if in time domain, if you do multiply, then in frequency domain, the two spectra get convolved. And that the second statement we can say right away because of this duality relation between the two domains. Okay, let us take one more example. That suppose in time domain I have these two impulses located at Td and minus Td, and their heights are a divided by 2, and this is, by the way, the magnitude of the signal. There is a phase component also, which is due to this 1 over j term, which is not shown here. Suppose in time domain I have a signal which looks like this. Now, this diagram is very much similar to the earlier diagram, except these two impulses were plotted in the frequency domain. And so we can say that if I am given such a signal in time domain, in frequency domain it becomes a sinusoid. But that sinusoid is a function of f now. It's a function of f, small f. And the role of the carrier frequency is now getting played by the time delay t of d. As I reduce the time delay here, these oscillations become more and more faster, and as I increase the time delay, as I increase the time delay, the oscillations become faster. As I reduce the time delay, the oscillations become slower and slower, all the way until if I make time delay equal to 0, so both these impulses come and sit on top of each other, then what it shows is that it becomes just the regular direct delta function, and for that this x of f will be a constant. It won't have any oscillations at all. Basically the oscillations became so slow that eventually the x of f became a constant. But anyway, so this is another way that we have applied this duality property. Okay, let us see. Now let us do one more thing before we conclude this video lecture, this particular segment of the video lecture, and here we are going to jump into the topic that we said we will be digging further into, which is the topic of modulation. Now, in order for us to fully appreciate the task that the modulator performs, we are required to first appreciate the Fourier transformation and also some of its properties, such as this duality property and so on. And so what this another property or the theorem of the Fourier transform, what it says is that if x of t and capital X of f is a Fourier transform pair, then this is also a Fourier transform pair, x of t minus td and x of f times the complex exponential with a phase component of negative 2 pi f td. And by duality, if I apply duality to here, this is also a Fourier transform pair. X of t times this complex exponential, basically what I had here on the right hand side, I brought it over to the left hand side, made it my time domain signal, and therefore this type of expression got transferred over to the the right hand side, the frequency expression. So these are two relationships of the Fourier transform which are quite important. Let us prove them one by one. Let us look at this very first sentence, first statement, sorry, x of t minus td. Now I would ask you to recall the shifting property of the direct delta function. Okay, so the shifting property, let us see. The shifting property actually was spelled out on slide number 8. It said that if I have any function, if I convolve with delta of x minus x naught, the function itself moves to x naught. And we had looked at this particular illustration to see what that shifting property tells us. And so now here in this particular example, this x is already shifted to by t of d. It has been delayed by t of d. Therefore, we can say that it must be this original signal x of t after it got convolved with an impulse at t of d. So this is directly from the shifting property of the direct delta function. But remember, the convolution in time domain is the product operation in frequency domain. What is the product for? Well, you take the Fourier transform of x of t, you take Fourier transform of delta of t minus td, and then you just multiply them. The Fourier transform of x of t is nothing but x of f. What is the Fourier transform of delta of t minus td? Well, that we did it over here. Delta of t minus td is this. We already did this. And so I'm just simply substituting that here. And so because of that, I can say that x of t convolved with delta t minus td, which is nothing but x of t minus td, is same as this expression here, which is actually this first equation. Now the second expression we can directly use by invoking the duality, or we can again do the same work and prove it uh, using the same type of steps that we have done here. I will leave that derivation of the second statement to you. Uh, as of now, let us concentrate on the second equation, which is known as the modulation statement. What it says is that if I have a signal whose spectrum x of f is a certain spectrum, and if I want to shift that spectrum to a new location which is f of c, remember f of c is called the carrier frequency, then the way to do that is to take my original time domain signal x of t and multiply it by this complex exponential. So for example, x of t could be the audio of some music, somebody singing a song, and maybe that musical audio is getting broadcast over FM radio. So what FM radio says is that musical audio, has a spectrum x of f, but that spectrum is centered at 0 hertz, and the transmitter cannot transmit a signal which is having the center frequency of 0 hertz. Such a signal will not propagate well over an antenna. But if instead that signal frequency is centered to some high number, then the propagation becomes much easier. And so that is what the FM radio does. It takes the audio spectrum x of f, which would be centered at 0 hertz, and it has to shift it to some carrier frequency f of c. For FM radio, it is typically in the range of 88 megahertz to 110 megahertz. In order to do that, this particular multiplication has to be performed in the time domain. And so that brings us to this slide, which is where we will end this particular video segment. Most often, whenever we talk about communication signals that are transmitted over the air or over cables, etc., most likely the transmitter is going to use sinusoidal carrier waveforms. Remember, we have used the word carrier earlier when we said the notation of f of c, where c actually represents carrier. And the reason why it is called carrier is because the sinusoidal signal, or in the complex domain, this complex exponential phasor, it is to be thought of as a truck or a goods train. And the information, in case of FM radio, it will be your audio signal, or in case of digital signals, it is the message symbols. In general, the information, either the message symbols or the audio or the video, these are analogous to the actual items that are being transported. What is the reason why we would need to use this carrier waveform? Why do we need to put this information in a goods train, which is this carrier? The reason is because these electromagnetic signals, which have this sinusoidal nature, they propagate well in the atmosphere and they propagate well over the cables. Furthermore, using a carrier frequency, we can place the transmitted signal at a desired portion of the frequency spectrum. And then, if suppose we have a small size antenna, we can kind of play around with the frequency. Maybe we can increase the frequency so that even a small antenna can send our signal in a powerful manner. And so the actual information almost always is transmitted by modulating this sinusoidal waveform. And the parameters that we have available for modulation are amplitude, frequency, and phase. And the corresponding modulation schemes in case of binary data are the schemes that we have seen earlier. They are ASK or OOK, FSK, and BPSK.